In this quick and short video, I want to show how you can create audio files or sound using Matlab code that sounds as close to real as possible. I know that it's probably impossible to get that very close proximity to real audio using just mathematical coding, but I want to show you how you can do a close enough job using Matlab. I am not actually using Matlab in this video. I'm going to be using GNU Octave, which is a free and open source software that is close to Matlab, and I'm using Ubuntu Baji environment as the Linux-based operating system to run this code. So with that said, let's go ahead and see what we can do to do that. And actually, I've created a folder where I'm going to be saving the files. As you can see, I have created a file which is empty right now. As you will see when I go into Octave, there's nothing in this code, but the audio files that I'm going to be creating will be saved next to this M file, which is, as you know, is a Matlab file to run functions and scripts. So in my environment, actually, let me go and find the folder here also. The first line of code that I like to write in Matlab is to clear the database or the workspace, and then close any figures that I might have. I don't have anything in here right now. And then clear the command window, which is this part in Octave. So the first thing I want to do is to create or define the first or the primary frequency of sound that I want to create. I'm going to call it frequency 1 or frec 1, and let's say 120, which is probably close enough to the first primary frequency of a drum head. I'm going to call this, let's call it primary frequency. Then I'm going to create some harmonics. And I'm going to call it harm, not that I mean to harm anyone. And I want to go from 1, which means when I multiply this harmonic array to the frequency, the first frequency is still going to be 120 hertz. And then I'm going to go every 1.5 multiplications of this frequency and go up to, let's say, 7. That's not a true or a real studied array of harmonics that is there. I'm just picking this kind of array as a way to create my harmonic frequencies. Again, this is not mathematically proven, so I'm not claiming any mathematical accuracy of this harmonics. So I'm going to, let's say, call this harmonics. Let's call this coefficients. And what I want to do is to say create an array of frequencies that I want to create in my audio file by multiplying this harm value that I created just the line above in line 3 by my primary frequency. And if I just run this piece of code, you will see that I have my initial frequency, which is 120, and then my line of frequencies or array of frequencies, which goes from 120, 300, 480, 660, 840. I mean, I could go higher if I changed from 7 to, let's say, 15, almost twice as much, and press F5 again. Now if I run frec again, this is not that, frec. Now I have more frequencies in my harmonics. Let's, for the time being, switch it back to 7. We can play with this later again. Now I have an array of frequencies, but what I want to put in my sinusoidal function is omega, which I'm conveniently going to call W, close enough to omega in the unique or the Greek letter alphabets. And I want to say, well, omega is always equal to 2 times pi times frequency. This is the angular frequency. So that's going to create the angular frequencies. Now, sound varies in time, so I have to create a time array. For that, I'm going to create TF, which is my final time. Let's say 1.5 seconds. And actually, to be more precise, what I want to do is to write in front of each line what they are. This is an array of frequencies, sometimes called temporal frequencies. And this is just creating angular frequencies, or frequency array, let's call it like that, and I'm just going to call omega to remember what that is. Now this TF is the final time, or the duration of my audio file. Duration. And now I want to create an array. But before that, I need to, when it comes to the audio files, you need to define a sample ratio. I'm going to call fs, which is pretty much what is known in many audio signal processing codes, fs for sample ratio. What that means basically is how many samples or data points you want to have per second of your audio. So I have determined 1.5 in here. I can change that anytime I want. And that means that for each 1 second of this 1.5 second audio file, I'm going to have fs number of samples. Let's call that 44,100 samples per ratio. I'm going to call this samples per second, or in other words, sample ratio. So with these two, I can go ahead and create my time array. I'm going to call it T, and I'm going to say this is a linear space from 0, the initial time, to TF, which is my end time. And the number of data points I want in my time array is going to be equal to TF multiplied by sample ratio. So that means that I'm going to have an audio file that runs from 0 or has a duration of 1.5 seconds, because I determined the end of my time array to be TF, 1.5 that I determined. And that is going to include TF 1.5 times 44,100 samples per second. And where I'm going to save the audio files or the audio data is, I'm going to call that a variable called x. And I'm going to call that initiate with zeros, because I don't want to have any audio in my audio file before I start creating the audios. Zeros, but how long this x is going to be? Well, it's going to have to be the same length of time, because if I want to plot this, it's going to be time in the horizontal axis and x in the vertical axis, but it has to have the same data points. But instead of going to the trouble of trying to say like multiply TF times fs, I just say make it size of t. That means not only the length of x is equal to the length of t, but also the size. Or if t is a 1 row and multiple columns, x is going to be also the same as 1 row and multiple columns, which will be demonstrated here. If I run this code, you see that time is 1 row and 66,150 columns. And x is also the same, but all the values in x at the point are 0, whereas time increases from 0 to probably at the end of it is 1.5. Actually, let's see what the last point of time is. It's 1.5. So that's what it's going to be. We're going to have time, and we're going to have x for the audio. So let me just write that. This is time array. And this is audio data array, for the lack of a better word. So what I want to do here is I'm going to create a for loop, and in this for loop I'm going to have a variable to count through the loops, or each step in the loop, that goes from 1 to how many frequencies I have. So I'm going to create a length of omega or W in here. I'm going to call end 4, I think, and that creates the end of my for loop. And at this point, in each step of the for loop, I want to add to my original x, which starts from zeros in line 10, a sine function of omega cnt, the frequency at each step, times time. So this is what I'm going to be doing. And at this point, I'm just going to add to the original x, and at each step a sinusoidal function. That means the sound is not going to be decaying over time. And let me, before going forward, show you what this will look like. I'm not going to keep plotting it all the time. If I run this, this is what it's going to look like. An audio file that represents this plot, which is very populated. So what I do instead of plotting that, I'm going to say do audio write. This is a function in Matlab that generates audio files. Give a name for that. I'm going to call this harmonics dot wave, and then so that's a file name that's going to be created in this folder next to my harmonics.m. There's going to be harmonics.wave. The data that I want to write in that, which is x, and the sample ratio, fs. It's as simple as that. So let's run this. You see in here, and also you can see in the directory that a harmonics.wave file is created, that I can either right click here and say open, and that's probably not a pleasant thing to hear. There's a reason for that. If I come here and say what is the max of x, is 4.811, and Octave, we don't see the warning, but if you run this code in Matlab, you will probably see a warning that the maximum value you have for your audio file in the audio write function is more than 1, and that's probably not an acceptable thing. So what I want to do to make sure that this error does not happen, or this problem does not happen, before I write the x in a file, I say normalizex by dividing that by the maximum of x. And if I run this code again, so let me actually write in here normalize x so that max of x is equal to 1, and I don't need to put a semicolon over there. And if I run this, and before I play the audio, if I just click or type max x in here, now you see that the maximum value of x is 1. So if I play this either from here or from the directory, it's not going to be an unpleasant audio. And there is a error. I don't think that's let me just try this again. Oh, that's not an error. All right. Sometimes this stuff happen. Although the VLC audio player was in repeat and it would just repeat the same thing, one thing I can also do is to create a longer version of this audio file by just saying create another variable. It's called x4, and put this in an array like this, x, 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 x. It's going to create 4 times the original x that I have in here, right, in line 16. So it's just going to be 4 times longer than my original x. And for the sake of not changing the previous code that I had, or the previous audio file that I created, I'm going to create a new one called harmonics 4. And in here, I'm just going to insert x4, and the sample ratio is going to be fs, the same sample ratio. So if I create, or if I run this code, it's just going to be 4 times longer, but it's a non-decaying sound. So another thing I want to do is to make it such that each frequency has a different and lower amplitude in my x variable in here in the loop as frequency goes higher. So for example, the 120 hertz, which is my primary frequency, was going to have the highest amplitude, and as I move forward in the frequencies to let's see what frequencies I have, to 300, 480, all the way to 840, the amplitude of these frequencies change. And that's because, you know, usually the primary frequency in a musical instrument has the higher volume, and as you go higher in the frequencies, the amplitude decreases. To do that, I mean, again, I don't have a proven mathematical function, so I just create mine. I say, let's call this CNT minus 1 times, let's say, 1.5 plus 1. This is just the mathematical function. You could put anything in here. I just want to put spaces so that it's more readable. Again, this is not a proven mathematical function. This is just something that works out for me, for my ears in listening to this music. So this should make the audio file that we create sound a little bit differently than we have heard. And in order to demonstrate that, I'm going to run this code again, And this time I'm going to come and play it from here just to show you that it is possible. So this is of course a little bit different than what we heard previously. So this is an ongoing audio file that doesn't decay over time. But if you have listened or if you've heard a drum strike, you know that the drum strike decays over time, so it dies off. And we want to see how we can create that. But before I go there, I just want to annotate my lines of code in here. This is an array 4 times the length of x, nothing fancy in here. And here I'm just going to write or output the audio files. Just these 2 lines do the same thing, except for different types of or different variables that I put in my audio files. So in order to create the decaying thing that I wanted to do in here, I want to create a variable called zeta for damping ratio. And in order to begin, I'm going to go with a damping ratio of 0.01. Just going to call damping or decay ratio. I'm just going to call it like that. And damping in vibrations and acoustics is an exponential function. I'm going to put this point star because I'm creating or I'm multiplying this sinusoidal function which has time as an array in it. And I'm going to put this time in my, or this t variable in my exponential term as well. So I need to put this dot star in here. Call it exp. And in this exp I'm going to have a decaying function. So typically it's something like zeta times omega and times t. I'm just going to put that here. I'm going to say minus zeta, which is going to be common for all of the frequencies, which probably is not the same, but when I multiply that by each frequency in the loop, that's going to increase the damping ratio for the frequencies as the frequencies go higher. So as with increasing frequency, the damping ratio, the decay ratio is going to increase because I'm multiplying the zeta by the angular frequency, and then multiply that by time. And for the sake of making it readable, I'm going to take that line to the next line. So let's try and see what will happen to the audio file after I multiply that by this decay ratio or decay ratio function. Let's run this. And as a matter of safety, make sure I didn't have any errors. I didn't. And let's run this from here. So now I guess you can hear this. One thing I suggest is that to not increase the volume of your computers or speakers too high, because it might hurt your ears. I don't think mine is very high. What will happen if I change the duration of my audio, my original audio? Instead of 1.5 seconds for each strike, let's call it 1 second. And let's run this again and listen to the audio file. That's one thing. And what if I make it longer? Instead of 1.5, which was original, let's make it 2 seconds. Run this, and if you want to run it from here, I usually like to use my keyboard to run it with F5, but you can just do save file and run. Do the same thing, and see that there is a wider time spread between each strike of the drum. I'm gonna switch it back to 1. That was quicker and faster. I liked it better. What I want to do is I want to decrease the damping ratio by 10 times. So instead of 0.1, I'm going to have 0.001. And run this code again. And run the audio file. Actually, I think I want to make it 1.5 so that it's easier to distinguish. And for this one, because the damping ratio is low, I'm going to make it 2. Run it again. And you can see that the frequencies don't like to die off as quickly as the previous sound. So this is not really a dry sound, and probably refers to a drum head that was not properly tuned. Now if I increase the damping ratio a little bit, but not quite as much. Let's bring it to 0.006 and run this code again. This seems like the sweet spot for the damping ratio of the harmonics that we had. So you can hear what's going on. And the other thing I want to do, like I promised in the beginning of the video, I want to increase the number of harmonics from 7 to, let's say, 15. Let's try again. And this time the sound should sound a little bit differently. So we have 4 times like this drum strike. So what we can also do is to play with the primary frequency. My original primary frequency was 120. Let's make it 60 and run this and play the audio again. And I don't know if the audio is coming across as loud as it should be, but you can see that this is kind of like a different drum. Now if instead of 120 or 60, if I go twice as high to 240 and run this code again and run it, see that first of all they're dying off faster. So one thing I can do probably is to decrease the damping ratio for higher frequency noises or audio and run it again. You see that this is a little bit different than before. And again, what we can do is to change the primary frequency from 240, let's call it 2400. We go 10 times higher in frequency. Although I have to do something, and I suggest that you do too, decrease the volume a little bit as I'm doing on my computer, because higher frequencies tend to be kind of like higher intensity and could harm your ears or hearing. So I warned you at this point. I'm going to wait a little bit for you to decrease the audio on your computers, and let's see. This is not actually on my computer, it's not very loud. Alright, so that is one. And what if I increase this to even higher? Let's go to 4000 hertz. Let's try this again, see what happens. Okay, and I'm going to increase the audio. And I want to do something else. I want to decrease the damping ratio even further. Run this and let this run for longer time. So this is kind of like another frequency that you can strike the whatever device that you have. So it's creating an audio file for you. So with that, let me just annotate this part. Let's create a decaying sinusoidal function to save or to add to the previous audio data. I think that is a short enough explanation of what's going on. And again, what we do here is that we decrease the amplitude of each frequency by a function defined in here, and that's not working well probably for higher frequencies. So let me actually make this a little bit differently for this high pitch 4000 hertz frequency. And let's run this again before I close this video, and let's play this. So that is that, and that's playing 4 times. Just as a matter of playing with this, let's make this 1 second per strike and run it again. That is a faster strike of, I don't know, a glass or something like that that's making this sound. Alright, with that, in a very short and quick line of MATLAB code, here again, like I said, I'm using Octave. You can create audio files in MATLAB and you can play them that are not necessarily close or exactly as the real audio files you will hear, but close enough that you know, it's pleasing to my ears.